Good morning. Good morning. Good morning. One sec. Sorry. Many problems. Good morning. I will say good morning officially in 1 second. Oh, we have, okay. Okay. Hold on. I will say good morning probably a second. Oh, okay. We're not even late. That's good. Hang on. Okay. Good morning. Good morning. Hold on. Okay. Hold on. Good morning, Alyssa. And I know you've been here for minutes and minutes and minutes. Good morning, Vivian. Same thing. Good morning, Jayla. Same thing. Good morning, Lakshmi. Good morning, me. Apologies. Again, I don't have the exams. I'm just going to keep saying that because I know it's bad, but I also want to be clear and move on. And you're not going to have to wait till next week to get them necessarily. I mean, as soon as I have them, I'll put them in Google Classroom. Hopefully, I will not spend my whole holiday on the holiday. Good morning, Newell. Good morning, Soad. Hello. Okay, we're going to just get to physics in a moment. Okay, let me just see. I was having electronic difficulties. So it looks like I'm not anymore. That's the one good thing. Okay, I think, hello. Okay. So good morning, Alyssa. Good morning, Soad. Good morning, Vivian. Good morning, Newell. Good morning, Lakshmi. Okay. Today, we're just going to continue with the new material for as much time as we have. And hopefully hopefully this new material isn't just going to be loose ends. Hopefully I'm trying to be a little bit big picture about it. And hopefully it will help you bring this semester to a coherent close, but also more to the point, what I want to do with the material today. And obviously, again, stop me if you have, wait, you just let me know. I'm sorry. You can hear me, right? Because I was having electronic yes. Okay. Thank you, Alyssa. Thank you very much. Okay. And thank you, Soad, very much. Okay. What we're going to do, what I want to get to is diagrams about forces, particularly because I believe at least one, well, I'm going to ask you this. I know the other section already in lab did a big board meeting and has work associated with what I want to do here. You may be in a slightly different place in lab, but I think you'll get, so let me ask you, could someone put in the chat, you've already done it? Oh, okay, that's even better. I get, does that mean it was already handed in and everything? Or if there was anything to hand in, maybe there wasn't anything to hand in, but you've done the diagram, the force diagram thing in lab. Thank you, Alyssa. Why am I confused? Slightly confused. Okay, we had, you did, okay. And was there anything to turn, is there anything left that you have to turn in on this? Or you're like totally done? Or put it, well, let me ask you this. What is the next thing that's, what I want to, the best thing I can do for you in the limited time we have is actually help you with anything that's due in lab. So let me put it a different way. What is there anything left ever due in lab that you, formal report 5. Okay. And that's for that's the slow down lab, correct? Like that's the down the inclined plane thing, or and up, the up and down. Yes. Okay. I'm glad I asked. I'm glad you told me that's very hard. I know, especially that formal report. So that's a big deal. So what I'm going to try to do today, and now that you've told me exactly, I'm glad we had this conversation. So I'm going to try to cater all of my discussion or my comments or whatever to that material to try to help you with that. Again, any of you can stop me at any time to back me up if there was still a loose end from the lab before, or you can push me forward. But okay, that's very, and I know, by the way, that lab must be a little bit difficult right now because it is, you're being pushed forward in the lab ahead of where you are here. And of course, that's what makes it science, that we do discover things first in the world and then we try to figure them out in our heads. But anyway, okay. Okay. So let's get going. So again, what I'm going to say now, I want to talk about forces and diagrams and things like that. But my focus here to everybody is going to be to try to say enough about forces and diagrams in an acceleration in my way, so that it'll put context for you and guidance for you on lab 5, which anybody who's listening to, which has to do with something going up and then back down a rough inclined plane. So I'm going to try to sort of get to rough inclined planes in general today. But let me again give you my perspective. Okay. Hey, I don't know what just happened. That's not what I meant to do. Okay. Okay. First thing I'm going to read this out. So I'm trying to give you a package of the 3 laws that really tells you how to dive in and solve problems, whether from experimental data or theoretical data. So the first thing, so, there's 3 laws, right? The first law I want to say is, the first law is almost like the control law, the base case law, almost the counterfactual law. The first law tells us what to well, so I'll just read it out loud. Newton's first law tells us what would or will naturally occur with a mass by itself. It tells us how an isolated mass tends to move naturally, like if it's isolated, if it's not being interfered with or affected by or influenced by any other mass, right? So if you just have a mass by itself, not interacting with any other mass, what can we expect it to do vis-a-vis motion, vis-a-vis space and time? And the answer, according to the first law, is that isolated masses do not spontaneously change their velocity. Okay, I don't want to dwell on this for too long anymore. In a way, most of the beginning, the bulk of this semester, in a way, has been trying to probe this idea. And I want to now look at the underside of the idea. But this idea says what you should expect of a mass by itself is that it will keep doing whatever it was doing motion-wise, that If it has a zero velocity, it'll continue to have zero velocity. And by the way, that's like the not surprising part. That's the part we sort of all almost don't feel like we need physicists to tell us. If we walk into a room, we see something sitting on the table, we're going to expect that it continues to sit on the table. It's not going to spontaneously like start like sliding off the table, like assuming the table's, or I shouldn't even, whatever. I mean, assuming the table's not tilted, et cetera, et cetera. But what this law is really also saying is zero velocity, the fact that we would not expect objects to change their velocity if their velocity happened to be zero. What this law is also saying is there's nothing special about zero. It's saying if you walk in to a situation and see an isolated mass by itself, not interacting with any other mass, so i.e. not touching anything else and not being subjected to some like gravitational pull from planet Earth or something like that, which is unusual. But if you see an isolated mass and it happens to be moving, so let's say maybe a hockey puck like that happens to be sliding at a high velocity along really, really super smooth ice, like so smooth that it's like barely roughly affecting that hockey puck, or even better, a hockey puck on a really smooth cushion of air, like as in on an air hockey table, which is a better example, right? So a hockey puck, an air hockey puck that's just like careening along, doing its own thing on essentially nothingness, right? Or if you can abstract this, like say a meteor in outer space, which is like a harder example to be familiar with, but certainly a very real example, like some rock in outer space. In other words, an isolated object that's not touching anything else. What we're saying in the first law is that if we happen to take a photograph or walk in on such an object that happens to have some non-zero velocity, happens to be moving in at some speed in some direction, we should not expect that object to change its velocity spontaneously any more than we should expect a sitting still object to change its zero velocity spontaneously. We should expect a moving object to keep moving the exact same way it's moving, same direction, same speed. Now, I don't want to spend the whole class on this because in a way we've spent the whole semester on this. But the reason we've spent the whole semester, and I'm sure that's like annoyed some of you, and I understand that, is because this is actually the central idea of physics, and like in some ways the hardest idea of physics. It's the easiest to think we get at some level, but the hardest to get fully. And I'm telling you this right now, honestly, I hope to see you all for a couple more weeks and for a whole other semester. But if ever any of you I never saw again, if there's one idea I could get you to walk out of this course with, it is this idea that zero velocity is not special. Sitting still is not a special state of affairs. Anything we all believe about sitting still, like we believe it takes effort to get something sitting still, to stop staying still, right? We intuitively all, I think, from our experience, from our brains, we're smart people, but even like just from living in the world, we tend to think that if you want to change, if you want to get something into motion, you got to like do something to it, right? And that's correct. That is correct. But what I'm here to say, what the first law is here to say, is that that's also correct of any other velocity. If you want any velocity to change, you have to do something to an object. Objects don't spontaneously change their velocity, whether their velocity is zero or not. In other words, zero is not a special number. In other words, zero is in the eye of the beholder. In other words, and this is Galileo again, right? Like whether something is moving or not moving is totally a matter of who is observing it, who's measuring it. Things are not actually moving or not moving in and of themselves. They are only moving or not moving in comparison to other objects. So in other words, no object absolutely is sitting still or is not. And so in other words, there is nothing special about the zero velocity state. So anything we've ever believed about it, if you believe it's hard to change an object from zero velocity to some other velocity, then what we're saying here in the first law is it's just as hard and just as unexpected, unnatural, impossible, in fact, for an object to spontaneously slow down as it is to spontaneously speed up. It's just as difficult for an object to spontaneously curve as it is to go straight. That's why curveballs in baseball are interesting, like seriously. Or that's why you can play air hockey, because you know what the puck is going to do. You know it's not if it's going toward you, your brain and your eye, like, or if you play any sport at all, right? Or if you watch any sport at all, you intuitively know what objects are going to do because you know what they're not going to do. If an object's going along like this, you know it's going to keep doing that until it whacks into something or until grass starts taking over. Like if it's a soccer ball, like if grass starts, like resisting it and slowing it down or something. But things do not naturally slow down any more than they naturally speed up. Objects maintain velocity when they are left alone, right? The first law says if you're not in the presence of a net external force, i.e., if you are not being influenced by a second object, then you'll just continue to do whatever you were doing, whether it was sitting still or moving. Making something move is no harder than making it slow down. What's hard, and now I'm going to turn the page, okay? I know I'm yelling because it's like, so, you cannot believe how much everybody thinks the hard part of physics is math, and everybody thinks like all the chapters that we don't have time to get to this semester are the really hard physics or something. I'm telling you that what's actually hard about physics is getting our minds around this idea and actually believing it at all times, even when it's inconvenient, and knowing how to use this idea to set up the equations that we think we're lacking and set up the diagrams that we think we're lacking. And once we do that for any kind of problem, no matter how hard, then we just turn the crank and the stuff happens. The hard part of physics is not math. And the hard part of physics is not details. And like the hard part is actually seeing how much this idea pervades everything. So I'm going to turn the page in a second, but the flip of what I'm saying is that forces do not create motion. Forces do not induce motion. Forces, the second law and the third law that we have to like start diagram, they don't tell you how to predict velocities. They don't have anything to do with velocities. That's why all the diagrams in the lab that you already did in the board meeting that this class did, you notice like even objects that had initial velocities, even cannonballs that were shot out of cannons, or footballs that were kicked by legs, or what was another one? There was some kind of sponge or something on a desk. I forget. It was some kind of object that was on a desk that was careening along along a rough desk because someone had pushed it a while ago, but now it was just careening along. So it had initial velocity. You notice initial velocity never goes into force diagrams. Force does not produce velocity. Force changes velocity. Force produces acceleration. That's why so much of this course so far, for good or for bad, has been about really like mathematically like playing with or analyzing or scrutinizing the detailed distinction between velocity and acceleration. Physics is really about that. It is about studying, is about our ability to study motion through understanding changes in motion, accelerations. If there's no net unbalanced, if there's no net external force acting on an object, there could be velocity, no problem. Velocity never has to be explained. But what there will be, if there's no net external force on an object, is there'll be no acceleration. There'll be no change in velocity. Like that's what I'm trying to say here. Okay, so now I'm going to turn the page, right? So the way we do physics is we figure out the acceleration on any given mass. We figure out the acceleration on any given mass and then plug it into all the constant acceleration equations that we've spent all this time in the semester like playing around with. The whole goal in physics is you look at a given object and you figure out its acceleration by adding up all of the vectors that represent all of the forces acting on that object, right? So the second law, sorry. Okay. Just to quickly say, what I really want to get to here is how to, believe it or not, all the action in all this is in the diagrams. I mean, the second law is the mathematical law, to be sure. And in fact, let me remind you what the second law, which is written on the first page of the notes today. The second law, to be sure, is this. The second law is, sorry, someone's here. Sorry. The second law is the problem-solving law. Like, for sure, once we, you know, when we're really doing physics, and when we're turning through a bunch of equations and algebraically manipulating quantities and getting numerical answers, all that action is contained in this second law that says net force equals mass times acceleration. For sure, it's the law that you have to use in the biggest way on, say, lab 5. Net force equals mass times acceleration. Just a quick, and of course, this is what we need the most practice with whatever time we have left in the course. Like we're going to be practicing in different ways this one. And that's what's happening in lab 5 is you're practicing and applying this one. But let me tell you, I mean, you can see it's a deceptively simple looking law. Like all laws in physics, the reason it's so powerful and so useful, and the reason it never goes away in physics, the reason it's the core of physics, this law, is because it's so simple. The fact that it's simple doesn't mean it's easy, and it doesn't mean it's simplistic. It just is simple. It's very easily misread. Like a lot of people think it might, I mean, the F stands for force, the M stands for mass, the A stands for acceleration. I kind of think that most of you kind of know that by now, probably. Okay. And the big sigma sign before the F means add up all the F's. So what this is really saying is net force equals mass times acceleration. The sum of all of the forces acting on an object equals the mass of the object times its acceleration. And it's also the case, I think I briefly said this yesterday, or Monday, it's also the case that I put arrows over the F and the A to reinforce, to explicate that force and acceleration are vector quantities. They not only have magnitude, but they have direction. More specifically, they can act on more than one dimension at a time. But when either one of them, when acceleration is two-dimensional or when force is two-dimensional, that just means it's acting on as two one-dimensional quantities independently yet simultaneously. In other words, those arrows are acknowledging the fact that force and acceleration can have components along a y-axis, along an x-axis, along a z-axis, and each individual set of components along each axis can either point positively or negatively. Honestly, that's really, really what I'm getting at with those arrows, is that negative signs matter along each individual axis. So what we're really saying here, put one last final way, and this is really important for lab 5, by the way, what I'm about to write it down. What this equation really means with the arrows in it, it really means that simultaneously, this is true. Sorry. I mean, I'm writing these small, but it is a big deal. I mean, it is a big point. To say net F equals MA with arrows is really to say that for any given problem that occurs, say, in the two-dimensional plane, like your inclined plane in lab 6, it's saying the sum of all the forces in this axis will produce the acceleration along this axis. And that's like one set of physics that's happening. And then simultaneously, yet independently, whatever sum of forces are happening on this axis, on a perpendicular axis, on some other axis, whatever sum of forces are happening on this axis equals the acceleration along this axis. That's what it really means, the arrows, that F net equals MA is really a set of simultaneous equations, one for each axis of space. And along each axis of space, negative signs matter. Like force is going this way, force is going this way might be denoted positive, while force is going the other way would be denoted negative. So when you add up forces going to the north with forces going to the south, you actually, the numbers end up looking like you're subtracting, if that makes sense. Like negative signs matter is what I'm saying here. Now, one last thing I want to say about, I mean, this is the powerful law. This is a law that generates all the math that we do. But it's hard to, but what it's saying is the sum of the forces acting on an object produces the acceleration of that object. So the M in this law is always the receiver. It's always our object of interest, as you might have said in the lab. It's our object of focus, our object of concern, our object of interest. M is the object to which things are happening, the object that is being pushed or pulled, and therefore accelerates in a certain direction at a certain rate in response to those influences. In other words, this doesn't mean, like a lot of people, like when they see this on t-shirts and stuff, or this doesn't mean that the more massive you are, the more you have force or something. It doesn't mean the more massive you are, the more you generate force or something. It means that the more forces are acting on a mass, the more that mass will accelerate. Okay. So this is the mathematical law. This is the law we have to use. But where many physicists or physics students tend to get concerned is, how do I set up the equations? Put another way, okay, if you add up all the F's acting up, put another way, what's always complicated about this law is the left side. The left side is where all the action is. The left side of F net equals ma is where we have to ultimately write all of the forces that are acting on an object along a certain axis of space. And the question for most people is, wait, how do I know what to write down? Like, what are forces? What aren't forces? How do I know what direction they're acting? And how do I identify the forces? That's actually the hard part of this. And that is where the third law and diagramming really comes into play. Most people, diagrams are to forces as graphs are to labs or something like that. Like, everybody hates them, and everybody kind of thinks they're just like a silly little, I don't mean everybody, but a lot of us can hate these diagrams at first and think they're just kind of like a weird academic thing that's like in the way of getting at the problem. But actually, the diagrams are the problem. If you really know how to set up a force diagram, you've done all the hard work in terms of setting up the left side of F net equals ma. And then it just becomes simple algebra or simple arithmetic from then on in. Hence, I'm going to turn the page now and get to the third law and to diagramming. Again, I know you already did. I know this class already, and I appreciate it. I mean, Alyssa told me, thank you. And that's points. I know you already have done this on a introductory level in the group discussion lab 4, but the diagrams make all the difference in the world. They are the kernel of lab 5. So please indulge me. I'm going to, I'm trying to, I want to show you how to do, if you can really understand the diagrams in lab 5, then you really can do lab 5 with all, and get all the numbers and everything. So I'm going to go to the next page here. And you'll notice, I'm assuming you have Newton's first law, Newton's second law, Newton's third law written down from 2 days ago. And if not, please get the notes from Google Classroom or watch the video. Like 2 days ago, I just kind of tried to explicitly tell you in my words what the laws are. Now I'm sort of trying to tell you how we use them. So these are not the words of the law. These are my description of their use. So Okay, I'll just read this out loud. And so what I'm saying here, so I'm reminding you what this last page said a second ago. And again, please stop me if you're losing me, or if you're losing me either way, either because I'm going too fast or just because it's like too theoretical or something. I know that's a concern sometimes. But the last page I was yammering about really about Newton's second law, and how Newton's second law ultimately tells us the effect of forces. Newton's second law tells us what forces do. What do? They accelerate masses. And again, let me remind you, acceleration is the whole program here, because once you have a value for acceleration for any given mass, then you plug that value into all the equations that we've gotten all semester, and then you can predict where the object is going to be when, which is the whole point of physics, right? So a big bulk of the semester was sort of analyzing what acceleration means and what all the implications of acceleration become. Now we're sort of back retro engineering and saying, where did acceleration come from? How can we know the acceleration of an object in the first place? And the answer is from all the forces acting on it. So the second law says the forces acting on an object, on a mass, give you ultimately its acceleration, right? That's what the second law tells us, that if you want that the forces acting on a mass tell us the mass's acceleration. Now, the third law, oddly, and maybe you might think the order of this is funny, but it just is what it is. The third law is telling us really what forces are. It's telling us how to recognize a force in the first place, how to identify a force in the first place. Ultimately, due to the third law, we are enabled to draw two different kinds of diagrams of situations. And the diagrams nail down what is or is not a force, where the force is coming from, what the force is doing, what direction it's acting in. And those diagrams ultimately enable us to have a clear, confident picture of F net, of sum of the F's, which then gets plugged into the left side of F equals MA and gives us A. Okay, so the whole thing might seem very backwards to you. Maybe it is, but it's kind of like we're studying effect and then backing up deeper and deeper into the causes for those effects. We want to know A, so we need to know the F net. We want to know A, so we need to know all the F's on some M. And if we want to know the F's, we need to look at the third law and particularly diagrams. Now, so I'm going to get to the diagrams now. And again, I know, you've already struggled with these diagrams in your own mind. Now I'm trying to give you my take to hopefully solidify. What was I just going to say? Notice here, I said something about the third law. I didn't say what the third law is right here. Remember, the third law, in short, is I push you, you push me back with exactly the same magnitude. That's what the third law is, right? It's the action-reaction law. But please understand, you have to sort of word it right. It's very easy. All of these laws are very easy to underestimate or misunderstand. The third law says if I commit an action on you, you commit a reaction on me. So what the third law, I guess what I'm really saying is, Okay. So again, like the third law is I push you, you push me back. Just to be clear, what is this really? Oh, I'm sorry. One last thing. Sorry. Okay. The third law is I push you, you push me back. What does that really mean? It means ultimately for there to be a force. What a force is not a velocity, and a force is not an acceleration. A force is not a type of motion. A force is not a description of an object. A force is something that one object does to another object. That is what a force is. A force is a push or a pull that one object exerts on, enacts on another object. In other words, a force is it's an interaction. It's an interaction. It's not a description or a property or like a modality or something. It's much more like a verb than it is like an adjective, and that's an analogy. But it involves something being done to something else. So it's an interaction between two objects. And when we say objects in physics, we mean it. I mean, you're really going to see this, why I'm getting so excited about this, when you take 204, quark Willing. It's an interaction between two identifiable, material, countable, noticeable masses, particles, things. Like you can't, in other words, a force is not something that something just has or gets just like from outer space or something. A force is something pulling or pushing something else. And according to the third law, it's symmetric interaction. If I pull you, then you necessarily pull me back in exactly the same way. So if you think about it, what this really is a very familiar idea. The reason I'm like screaming and yelling, and again, you'll see, like, if you ever think that I'm getting if you ever notice that physics seems like we're saying the same, like if you ever feel like we're not getting anywhere in physics, and I can respect that and I can apologize for that. In a way, I mean, you are getting somewhere if you feel that way, because physics is the same idea, just being pushed through a more and more advanced filter or more advanced lens or something like that, and the same idea being applied to more and more advanced circumstances. But it is, if this sounds familiar, it is the same idea again. In other words, once upon a time, we screamed at ourselves that velocity is not something that an object has. It's a relationship between two objects. And in fact, we said it was symmetric. Like if I'm going 65,000 miles to the east past you, then you're going 65,000 miles per hour to the west past me. And we said neither one of us is any more correct than the other. It's just a relationship. And whether you want to look at that relationship from my frame of reference or your frame of reference is totally your choice in physics, as long as both those frames of reference are unaccelerated. Well, now we're saying a very similar thing about what a force is just an interaction between two objects. It's just an interaction. And you can look at it from one perspective, or you can look at it from the other. You can look at it as me pushing you, or you can look at it as you pushing me. But at the end of the day, we're just pushing each other. And there's no way to distinguish. And neither, in other words, it's like, you know what? I married my wife on the exact same day that she married me. Can you believe it? Like seriously, my wedding anniversary is October 20th. So's my wife's. Coincidence? I think not, right? Like, I mean, and I'm very blessed that way. But I mean, like, I married her. She married me. That's just a perspective kind of remark, whether you say it one way or the other. We got married. That's it. It's an interaction. Force is like that. Force is a symmetric interaction, a push or a pull between two objects. And to take it one step further, if I pull you, then you pull me back. Like if I pull you, then you pull me back. If I bring you toward me to the east, then you bring me toward you to the west. If I push you away, then you push me away. It is a symmetric interaction. Same magnitude in both directions, just different directions. So this is really the sixth form of Galileo's principle of relativity. It's another sort of more advanced way of saying the same thing, which is just that in the world, there are these relations, and you shouldn't get bogged down from which vantage point you look at these relations. You got to realize that they're just relations. But now let me go a step further. And this is where you get into the diagrams. And I know I'm screaming, but we're kind of on time. Okay. Now, and again, I know for many, I know this all sounds very abstract, like, come on, help us to solve the problem, help us solve the problem. And I really do sympathize with that, but I really, to some extent, and that's my imperfection, but to some extent, if you just bear with me, I think like the hardest part of solving problems is beginning them. I think we all know that, is how to set them up. So really all this talk is I'm trying to get to show you how to set up problems. So like whether it's lab 5 or lab 4 or lab 5 or whatever, when you're trying to, when you're looking at a situation and asking if you're focusing on something like the mass that's going up the inclined plane in lab 5 or coming down the inclined plane, and and at any given moment, that's what you're supposed to be doing, is focusing on that mass, that block, or that marble, whatever is like making its journey. You're focusing on that thing. You're focusing on it at one given point in space, at one given point in time. The Newtonian program is like that. Like you're taking a mental snapshot of this block, this mass. And in order to make predictions about its acceleration, you have to ask yourself what forces are acting on it and how are they acting? So you get into this question like, well, someone pushed it initially, someone like tapped it and gave it this initial velocity so that it went up. Is that a force in my diagram? Does that go into my system schema diagram? Does it go into my free body diagram? Well, the answer is no. First of all, like in lab 5, the initial, and again, I know to some of you I'm speaking completely abstractly now because you might not exactly remember or know when I'm talking about lab 5, but I'm just saying if someone pushes something up an inclined plane and now you are focusing on some moment in the journey of the object up the inclined plane, at that moment that you're focusing on the object, that finger that flicked it is no longer touching it. So that finger that flicked the object going up, oh, it gave it an initial velocity. Oh, it's relevant ultimately to some calculation that you're going to do. It's going to affect something, that initial velocity, but that's just exactly what it is. It's an initial velocity. What it isn't anymore is a force. And what it isn't anymore, therefore, is any kind of contributor to acceleration. It may have given a velocity at one time, but it is no longer contributing to the changes in velocity. It's not going to contribute to an A. It is simply a V naught. How do I know? Or why am I saying this? Or what's this got to do with this? I'm saying that really what we see from the third law, a force is anytime one object interacts with another object. Now, there seems to be exactly one scenario, one example, or one phenomenon where it seemed from our life experience in the world of mechanics, of classical mechanics, of the physics, of Newtonian physics that we're doing here, there seems to be one context in which two objects somehow can interact with each other without touching. That one context is gravity. And I believe in it only because I experience it every single moment of every single day, just like you. That is apparently, evidently, historically, if I let something go near the surface of the earth, it falls down. Evidently, all objects all the time are being pulled toward the center of the earth by the earth in some fashion that doesn't seem to require the earth to touch those objects in order for that to happen. That's the one context of mechanical physics, in which interaction seems to be able to occur without physical contact, without touching. Okay, this is very important. What I'm really trying to say here is a force is an interaction between two identifiable objects. Other than gravity, in order for two objects to interact, in order for two identifiable, massive material particles to interact, in order for two masses to be pushing or pulling each other, they've got to touch. So with one exception, anytime you're asking yourself, should something go into a system schema? Should something go into a free body diagram? Is something acting as a force on my object going up the inclined plane? If you're trying to identify what is acting as forces on that object at some moment, the answer is all and only things touching the object plus gravity. It's always plus gravity. In fact, for this reason, we always actually put gravity in first into every diagram. Gravity is this one phenomenon that seems to happen without touching. So we put it into every diagram. It's there in every situation. Every object seems to be pulled towards the center of the earth without the earth touching it. The earth is always affecting every single object. So every object we analyze, the first thing we do, if we're drawing a system schema, we right away draw a circle representing earth, and we draw a line to our object of interest. Like, and I don't even, if it's a system schema, I don't even care where we put the earth, but we put some circle that represents planet Earth, entire Earth, center of Earth, whatever. And we draw a line going to our object of interest. I always do it first because it's always there, and it's the exception. It's the one exception to the big rule. Gravity seems to be the Earth seems to be able to pull on things without touching them. Notice I am saying the Earth. I'm saying even that pull that we call gravity is a pull that's coming from an object called the Earth. Now, how is it coming without touching? I don't know at this stage. It's so crazy that that's happening. The only reason I'm asking you to believe in it is that we experience it all the time. Gravity is such an exceptional force. It's so bizarre that this happens that it kept geniuses up at night for centuries. Like gravity is, I mean, we have more to say about it later, and in physics 204 and all that, like we've discovered, the world has discovered many things about gravity, but it needed to discover things about gravity because first and foremost, we just experienced this phenomenon that we call gravity, which is a pull happening without touching. After you put that into any diagram, then I'm saying, and I'm going to turn the page now, I'm saying after that, the only things that should go into a diagram are touches. Like that's the rule. So, okay, let me get to concrete now. And I'm going to do this again in the context of lab 5. So I'm going to start giving you diagrams and like stuff about lab 5 now. But okay, yeah. And again, so I'm, well, sorry. Okay. Okay, so okay, so what I have here, this is not a diagram, right? This is a picture, just so we're all on the same page. This is a picture of a situation I want to analyze. Again, I believe it's your lab 5, but it could be, so we have an inclined plane. I'm partly drawing the plane just so you see how, in my mind, the plane is oriented like the way that it's oriented, right? I mean, yours could be another, but this now all my so any diagrams I draw are going to be consistent with this picture. Again, yours might be the reverse. It's totally okay, just so you can follow mine. So I have a slide. I have like a plank of wood or whatever, and it's angled from the horizontal at some small known angle known as theta. I draw the little jaggedy, stupid like etches on the slide to indicate that it's rough. In fact, let me also say, so whether you're up to this point or not, some people will put a mu, the lowercase Greek letter mu, to indicate that there is some amount of roughness of what we'll ultimately call friction, a coefficient of friction. So I'm just trying to indicate that one way or another that this slide is rough. We've got a block on it, a block of mass m. So that's the mass that I'm going to focus my attention on. That's the mass whose acceleration I ultimately want to predict and calculate and so forth. And I'm picturing some point in space, some point in time where the object happens to be on its way up this slide, right? Like, again, if you've done the lab or you know the lab I'm talking about, then the whole situation is like a round trip. Like we flicked some mass, it went up a slide, it eventually came to a stopping point, and then it started going its way back down. It made a round trip. We're right now examining one moment in that round trip, and we're deliberately right now examining a moment that happens to be during the ascent, the way up, okay? So what's known as the mass of the mass, sorry. Okay, sorry. What's known as the mass of the mass, what's known as the angle of the angle, what may also be known or is the initial velocity of the mass. Like that totally could be like someone flicked it. So it didn't start from zero. It started like 15 meters per second or whatever. Now, presumably, just intuitively, I think it's probably fair to assume that the mass is slowing down. It's eventually going to come to a stop, come back down. But whatever flicked it, whatever sent it up is no longer touching it. So it's just like on its way up this rough inclined plane. And what I want to do is draw diagrams of this situation in order to set up like the purpose. What I want ultimately, the ultimate question of any physics question now really is like our goal is what's the acceleration of this mass at this point. And so I'm going to get that by doing F net equals ma. I'm going to get F net by drawing proper diagrams. Like that's like the idea. And so I'm going to do that in 1 second. Again, just to be as clear as possible with the 20 minutes that we have left, this is not the simplest scenario at all. Like if I were literally just beginning my life of analyzing force now, I would first start with something just in free fall or something like that to be like, so, but you as a group, in my understanding, have already had the challenge of going through that. I'm not arguing that this is the simplest scenario. I'm arguing that it's a realistic scenario, and I'm giving you a method for drawing diagrams that will work for any scenario. First thing I'm going to do before I even give that method or draw the diagrams is what I always do in physics. I'm going to make some choices about my perspective and my coordinate system. That is, since this thing is I'm going to decide. Yeah, I'll decide, since this thing is going up, I'll call, well, actually, this is a choice. I'm going to choose, now this is a choice, and you don't have to do this. I mean, you do have to make a choice, and you have to be consistent with it. You can make a different choice from mine, but you have to make a choice. I'm going to choose to call down positive, and I'm going to call up negative. Now, it's a slightly strange choice, but I know some things are going to be happening in the upward direction. Like I know the thing is moving up, but I know some things are going to be happening in the down direction. Like I know gravity is going to be pulling down, and I know gravity is going to be very important in this. And honestly, to tell you the real truth, so I know there's going to be positive and negative signs. There's no way to avoid some negative signs here. I'm going to choose to call down positive, basically because I'm predicting that I'm going to have more things that are relevant happening in the down direction. Like I think gravity is very relevant to this problem. I think I'm going to actually have fewer negative signs to hassle me if I call the down direction positive. If you really want to know really how I'm making my decision, I'm doing something I always do in physics, which is I'm actually predicting that this thing, and maybe, I don't know if this helps you or not, but I know this thing is moving up. but I believe this thing is accelerating down. I think we're going to find that when we do our diagrams and do F net equals MA, I think we're going to find that this thing is accelerating down while it's moving up. Is that a contradiction? No, I'm simply saying in English, I think this thing is slowing down, not speeding up. I don't think it's gaining speed on the way up. I think, in other words, I think it's just like if I just threw something up, something can move up while it accelerates down, i.e. it loses velocity. I'm pretty sure that's what's going to happen to this thing, because this thing, I mean, it's got gravity on it. And the only other complexity is it's like also got friction on it. But frankly, I think the friction's also going to be, I mean, I don't know what you think, but I think the friction's going to be acting against it also. So I think this thing's going to be slowing down. That's why I think it's going to stop and come back down. So I think the acceleration, which is what we ultimately really care about and we're solving for here, is going to be pointing down. So in order for me to get a number that's positive and clean and to have as few negative numbers as possible, I'm making the decision that anything that points down is positive. By the way, last thing, and this is, you got to do this for the lab. If you're still with me for lab 5, like you've got to make, before you start diagramming anything, you got to make a decision like this. And you probably know, if you're already into lab 5, we're ultimately going to have to compare this. Right now, I'm looking at the up trip. Ultimately, I'm going to have to make a comparison between this up trip and the down trip. And if I want to make a comparison and compare their two accelerations, which is really the goal, I really want to find out what's the acceleration up, what's the acceleration down, how do those two different accelerations determine the time up and the time down. If that's what I'm going to do, I want to use one consistent coordinate system to describe both. Otherwise, I can't make a comparison. So I want positive and negative to mean the same thing for both. So frankly, even I'm choosing this also so that I can use this same choice when everything on the next trip, when everything is coming down and it's obvious that everything is coming down and I really want to make down positive. I'm anticipating that as well. And so I'm going to call down positive. Again, honestly, it's one of the hardest parts of the whole problem is to realize you got to do that. You got to make a choice. If you don't like my choice, that is fine. You can make down negative, but then stay consistent with that all the way through the comparison and be careful. Like, okay, anyway, so that's my decision. Now I'm going to draw some diagrams. I'll also tell you, in case I run out of time, all my fuss about positive and negatives really matter for the math and really matter for solving lab. They won't matter for system schemas, which is the very next thing I'm going to do. They're going to ultimately matter for my free body diagrams and all of that. But first, I'm now going to go to system schema. So, okay, so. Okay. The purpose, so the system schema is our first step to figure out actually what is a force and what is not a force acting on our mass of interest. We're literally trying to make sure that we get every force into our list, and we're trying to make sure that anything that we might think sort of might be a force but isn't, doesn't go in our list. We're really trying to like separate the universe here in the system schema. We're all about making sure we have an exactly correct list of what the actual forces are acting on our mass of interest. Like that's our whole goal. And so, and the way we do it is it's totally about the third law. We totally say to ourselves, the only way a force can act on our mass of interest is if it's if it's interacting with it directly, which means either it's planet Earth. Sorry, let me back up. The only way a force can act on our mass of interest is if some other object is interacting with our mass of interest. So the first object that's always interacting with our mass of interest is Earth. So we always put that in the system schema. And then from there, we have to identify every single object that is in any way interacting with ours, i.e., every single object that's touching our mass. So we put in Earth and then anything and everything that's touching our object, but that's it. If we can, in other words, this is not, and so this one is not concerned with directions. It doesn't matter about directions at all. And it's also not concerned with mystery words. Like this is not the time to come up with words like friction or tension or normal, or like I'm not saying those are wrong words or that they don't matter in physics, but I'm saying that's not what this is about. This is about preventing us from just like believing that a force has to exist. For example, there is something called the normal force. Many of you have heard of it. It exists, like I believe in it and all that, but it's got a very horrible name being called the normal force. And it makes people think like it's just like normally there. And whenever an object is there, there must be a normal force acting on it. There's nothing like that in physics. For there to be a force acting on me, there must be an object pulling or pushing on me. If I can't name what the object is, then there ain't no force. Okay, so in order to draw a system schema, so I'm going to the next page. I'm looking at that. Yeah, in order. Okay, I'm going to read this. I'm just going to read it directly. And then on the next page, I'm just going to do it for, for our case right here. Again, the good news is our case right here, the lab is kind of like among the harder cases possible. So if you can get it, you can get anything. But here's what I'm saying now. In order to draw a system schema, we draw a dotted circle for our mass of interest, our object of interest, the mass M, right? Like whatever we're focused on, which in this case is the block on the inclined plane or the marble on the inclined plane, whatever. And we draw a solid circle for every object pushing or pulling on our object of interest. So every single object that's pushing or pulling on our object of interest, that includes Earth, we draw a solid circle. And then, so we have all these circles, and then we connect the circles with lines, okay, and with exactly two except this sounds very muddy, but it's actually very precise. What we always do is we follow something called the one touch, one line rule, always, but there's exactly two exceptions to that, but we always honor these two exceptions. You'll see what I mean in 1 second, but we're going to say for every touch, we draw one line. There's two exceptions, and you're going to see in a second. The two exceptions are gravity is a line without a touch. Gravity is, except for some reason, Earth can pull on me without touching me, but it still is pulling on me, so it gets a line. Okay. And the other exception you're going to see in a second is whenever two surfaces push against each other, when two surfaces push, like surfaces as opposed to like wires, push as opposed to pull, whenever two surfaces push against each other, that touch of surface push gets two lines. You'll see what I mean right now. Okay, this right here is the system schema. I have 7 minutes. This is the system schema for the mass on the inclined plane. This is the system schema. What's going on here? Well, the Earth, CE stands for center of Earth. You could say PE, planet Earth, or EE, entire Earth, but I just, something like that to connote that we mean Earth, the gravitational body, not Earth like dirt or ground or something. Because like sometimes things are sitting on the ground. And so that would be, so that's like something else. But so I have one circle for the center of Earth. It is definitely pulling on our mass. It gets a line because it's one of our two exceptions. It's not touching, but it is pulling, so it gets a line. Like line means pull, line means force. And notice, like I don't care where I drew the Earth. This is not about direction. These are not arrows. These are just Newton's third law lines. They're just meaning the Earth and our mass are interacting with each other. You could say the Earth is pulling the mass, and that's true. You could say the Earth is pulling the mass down, that's true. But the mass is pulling the Earth up, therefore, and that's true. There's just an interaction between mass and Earth. If I believe in gravity, if I want to ultimately have a force in my mathematics called gravity, I have to justify that by the fact that gravity is just a name for the force coming from this identifiable object called Earth. Okay, so that's that. Then I've got the plane, like the slide that the object's on. Well, that's an object. And that object is definitely interacting with our mass. How do I know? Because it's touching it. Like that simply. It is right now at this moment, our mass is on the plane is touching it. Now so it gets a circle. The plane is an object, it's interacting with our mass, it's pulling or pushing it or whatever. So it's exerting forces, so it gets a line. But this is a surface pushing on our block. Like the slot, like it's pushing, in fact, at a funny angle, but that's not my, but the plane is a surface, and the underside of our block or whatever is a surface, and they are pushing against each other. And whenever we have two surfaces pushing against each other, we draw two lines instead of one. I'm just going to note that here. Particularly if they're rough surfaces. Okay. Whenever two surfaces push against each other, they actually push against, well, whenever two rough surfaces push against each other, the fact is like they're pushing, so they're touching, so that's a force, so it's a line in the diagram. But it's actually two forces. Whenever, and again, this is not true of a fishing line pulling on a fish or something, but it is true of any time two rough surfaces push against each other. Because whenever two surfaces push against each other, like my hands are pushing against each other right now, or the plane is pushing against the underside of the block, they push like this. But if they're rough, then if you looked at them microscopically, you'd see all these bumps and ridges or nooks and crannies or whatever. And it would be like, and the nooks and crannies interlock with each other. So whenever two rough surfaces push against each other, they interlock, and it automatically makes it difficult for them to slide along each other. So necessarily, whenever two rough surfaces push against each other, they also lock and make for a rubbing force along one another. Whenever they push perpendicularly, they also push on the other axis parallel. The perpendicular push we call normal, simply because normal just literally means perpendicular in mathematics. So whenever two surfaces push against each other, we call that push the normal push. Normal doesn't mean it's always there. For example, something in free fall, there's no normal force on it at all. Me pulling up a fish with a fish line, there's no normal force there at all. Normal means perpendicular. So when two rough surfaces push against each other, the component of push that is perpendicular to the plane of contact, we call normal. And the component of push that is parallel to the plane of contact, we call friction. So whenever two rough surfaces push against each other, they really exert two interactions. One we call the normal force, or the normal interaction. That just means perpendicular, the squeeze, the push, the against. And the other, the parallel push, the rub, the slide, we call friction. This is the system schema for your lab 5. Because we only have 2 minutes, what I'm just going to literally do right now is I'm just going to draw. I'm not even going to talk. For the 2 minutes, I'm just going to draw the free body diagrams just to help you, push you along. I'm not even going to explain them. I'm just going to draw the correct answers right now as your reward for sitting through all of this. And they're key. So anyway, we'll talk more on whenever we do, but okay, so. Oh, yeah. As I say, because it's 12:05, I don't want to torture you. I'm not going to really attempt to explain these right now, but if you're thinking as a check against your own work or whatever, they might help. This is the pure diagram for the thing on its way up. N stands for normal, F stands for friction, like I was just explaining. And then if you were to break gravity up so that all forces had components lying along, if you were to call this like a y-axis and this in x-axis, then the components would be divided up the way they are in the second diagram. For the down trip, everything is exactly the same, except for the down trip, friction points in the opposite direction. Everything is the same except friction points in the, I'm just going to leave it at that. But obviously, we'll talk more about this somehow on Monday, but I'm just going to leave it at that for now because we are out of time. But hopefully this helped somewhat, somehow, some way. But I'm good if you're good, and have a great, super happy Thanksgiving. I will get the test back to you. When I do, I apologize again, and I'll stay here for any questions or whatever, but have a great Thanksgiving. Thank you. Have a great, yes, you too. And I'm here for questions if there are any questions. But